Hi, I'm going to present a summary and a slightly easier view of converting from grams to number of molecules and AMU. Okay, so this starts from your textbook, and Dr. Bishop has defined what an atomic mass unit is and what that is in grams. So I'm just going to simplify the equation a little bit. This means 1 AMU is equal to this small number, 1.660540 times 10 to the negative 24 grams. And what I'm trying to present to you is, what if on both sides, okay, I don't want small numbers, so I want to have a bigger number. If I divide it by the 1.660540 times 10 to the negative 24, just that number on both hand side, what will happen is that you'll find this relationship. Okay, I'm not doing anything to the unit yet. So the next relationship is AMU stays on the left, right? On the right, you still have grams. Okay, so on this side, notice that these two numbers, because I made them exactly the same, they cancel and they become a 1. On the left-hand side, if you did a 1 divided by 1.660540 times 10 to the negative 24, you'll discover this magic number again. We call it Avogadro's number. That is the 6.022 times 10 to the 23rd. Now, how it's done at different places, sometimes they give you 3 significant figures, sometimes they give you 4. I kept 4 because it will be, more correct, right? So what this is basically this many AMU makes a gram. Okay, so why do we use the Avogadro's number? Take, say, the oxygen atom as an example, right? We know its atomic mass is 16.00 AMU. This is what we call atomic mass. This is what you can find in the periodic table. And so one atom weighs this much, right? Now, what if you have a lot of atoms? What if a lot of atoms is the same number as the 6.022 times 10 to the 23rd? So notice, do you see this? You go from one atom weighs this many AMU. If you have that many atoms, if you have this many atoms, you basically just multiply this many, right? If I have 2, I'll multiply 2. If I have 10, I'll take that 16 AMU and multiply 10. Now, what if I have 6.022 times 10 to the 23rd? Or Avogadro numbers of atoms, then I multiply that. Once I do that, notice what is this? This is effectively the same thing as that, isn't it? What I meant, they're the same thing, right? Well, 6.022 times 10 to the 23rd AMU is a gram. So if I multiply that many for oxygen atom, then this many will weigh 16.00 grams. And what is this many? This many is giving a name called 1 mole. So what did we get out of this? Well, what we found based on this is 1 oxygen atom, okay, is 16.00 AMU in weight. So if I have a table, this is kind of not neat, but say on this side, I do number of atom, okay, and then here I do mass, okay. Over here, if it's 1 oxygen atom, is this many in AMU in terms of mass. What if I have Avogadro number of oxygen atom. What's Avogadro's number? That's 6.02 times 10 to the 23rd. This many number. How much does it weigh? That is 16.00 grams. Okay, good. So what is an Avogadro number? This is a mole. So basically, we just counted with the number that's going to turn AMU into grams. That is it. So if you have one oxygen atom that weighs that many in AMU, what you'll have is a mole of oxygen atoms will weigh that many in grams. So what if I have, say, one copper atom? Okay, you go to the periodic table, you look for its atomic mass, and what you'll have is, it is 63.55 AMU if I keep 2 decimal places. Okay, so this is on an atomic number basis. I'm going to separate these two things. Okay, what if I have 1 mole, that's Avogadro's number, of copper atoms? What would it weigh? You got it. It is 63.55 grams. So, lastly, what do you know? You know anything. Okay, anything. Let's just say its atomic mass is this number. It's cherry looking. Okay, so anything, what happens is this one atom of the anything is equivalent to cherry number of AMU. 1 mole of this anything is equivalent to this cherry number in grams.